There's a family of functions related to the one represented in the solvent. Just as the absolute value of x is its distance from 0, the absolute value of f of x, or, denoted here, the absolute value of f of x, gives the distance from the line y equals 0 for each value of f of x. The simplest example of an absolute value function is f of x equals the absolute value of x. The graph of the absolute value of a linear function in two variables is v-shaped and symmetric about a vertical line called the axis of symmetry. Such a graph has either a single maximum point or a single minimum point called the vertex. Take note, key concept, the absolute value parent function f of x equals the absolute value of x. First, we'll see it represented as a table on the left. Values of x in the left column, -3, -2, -1, 0, 1, 2, and 3. And the y values associated with those when input into the absolute value parent function. An input of -3 leads to an output of 3. Input of -2 leads to an output of 2. Input of -1, output of 1. Input of 0, well, the absolute value of 0 is 0, so an output of 0. And then we get to the positive side. The absolute value of 1, 1, 2, 2, and 3 is 3. As a function, we can state that f of x equals the absolute value of x equals x when x is greater than or equal to 0. We can also state f of x equals the absolute value of x equals negative x when x is less than 0. The graph of the absolute value of a linear function in two variables is symmetric about the axis of symmetry, in this case, the y-axis. The graph of an absolute value function has either a single maximum point or a single minimum point called the vertex. In this case, the vertex is a minimum point at the origin, and that's the point 0, 0. Problem 1. Graphing an absolute value function. What is the graph of the absolute value function y equals the absolute value of x minus 4? How is this graph different from the graph of the parent function f of x equals the absolute value of x? Well, consider what you might think on the left and what you may write on the right as you solve this problem. First think, make a table of values and graph the function. And then write first a table of values with some x's selected, -3, -1, 0, 1, 3. Note it's wise to choose some negative values and positive values to make sure that we do our best to get on each side of the vertex so we can accurately graph the function. Substituting -3 into the function, y equals the absolute value of x minus 4, we get an output of -1. When we substitute -1, we get an output of -3. 0 is related to -4, 1 related to -3, and 3 related to -1. We can graph these points and connect them with two rays, forming our absolute value function, V-shape, opening upward with a vertex or minimum point on the y-axis at 0, -4. Next think, use the location of the vertex to see how the graph has been translated. The parent function was not multiplied by a number, so the graph wasn't stretched, compressed, or reflected. And we can write our statement. Since the vertex is at 0, -4, you translated the graph of y equals the absolute value of x down 4 units. Your turn, part A. What is the graph of the function y equals the absolute value of x plus 2? How is this graph different from the parent function? And part B, a reasoning item. Do transformations of the form y equals the absolute value of x plus k affect the axis of symmetry? Explain.